Switching gears now, we're going to move into chapter 13, and we're going to start by talking about vector-valued functions. So this is just a new type of function that we're going to talk about. So it's a new type of function. And we worked a lot with functions in the past, all the way from Algebra 1. And typically what you're used to is what's called a scalar valued function. So the outputs are scalars. You know, for example, you might have f of x is equal to x squared. Right, that's a scalar valued function where your input, so the input is x, and it's a scalar, like 1, 2, 3, and then the output, or excuse me, this is the output that we can call f of x, or we could call that y, like y equals x squared, and that's also a scalar. And then you create the graph of all the possible outputs by connecting the outputs of different values of the input. Right, so we might have at x equals 0, we get 0, x equals 1, we would get 1, and then 4, and then 9, right? And so by connecting different values of the output, you kind of get the graph of all the possible ones. So this is an example for y equals x squared of a scalar valued function. So now we're going to talk about vector valued functions where the output, so the output of the function is a vector, and the input is a scalar. Typically we use t. The parameter t is our input. So let's take a look at what one of these vector valued functions might look like. So here we have r of t, and if you notice that notation is a vector. So the output is saying r of t is a vector. That's what that bold r means. Is equal to a vector from the origin, that's what this OP means, from the origin to the output point. So from the origin to a point. And that can be equal to, right, we have our I, j, and k unit vectors, and then we have a different function attached to each direction. So there could be some function that tells us the I component, some function that tells us the g component, and some function that tells us the k component. And each of these is dependent on t. So the inputs to all of these are t. So you input a t value into each of these, and the output is a vector. So let's just take a look at example 1 where it's asking us to sketch some of these vector valued functions for a representative range of t. So we're just going to plot enough t values so that we kind of get an idea of the picture being made. So here we have r of t is equal to t plus 1 in the I direction and t squared minus 1 in the j direction. So there's only two components to this graph. So we know there's only two components, right, I and j, so we know it's going to be a 2D curve. So it's in the xy plane because there's only x and y possible coordinates. So let's just try t equals 0. So we'll do r of 0, that's going to be 0t plus 1 in the I direction. So we'll just get 1i plus t squared, in this case is going to be 0 squared, minus 1 in the j direction. So we actually get minus 1. Minus 1j. So at t equals 0, when our input's 0, the output vector is 1i minus 1j. And so let's plot that up here. So 1i minus 1j. So I'll just pick that. So 1i minus 1j is going to look something like that. So that's at t equals 0. Now let's try t equals 1. So we'll get r of 1 is going to be 2i plus 1 minus 1, so 0j, so we just get 2i. So 2i is going to look like 1, 2. So that's the output vector there. Let's try 2. So we get, so that's going to be 3i plus 4 minus 1 is 3j. So 3 and 3. So that's going to be something that looks like that. Oh, sorry, that's t equals 2. We'll do one more. So for t equals 3, we'll get 4i plus 9 minus 1 is 8j. So we're quickly going to exceed the scale of our plot to get 4i plus 8j. So that's going to be something like way up there. And the way we plot this vector valued function is we connect the outputs, just like we did up here. We connected all the different representative outputs to get a smooth plot. So in this case, we'll get something that kind of looks like this. Oops, let me try to connect them better. And so you can imagine that in between the points we plotted are infinitely many vectors that connect to the points in between. So all of those vectors are in there as well, and those would be for vectors where, or for outputs where you put in like t equals 1.1, 1.2, 1.3. And if you connect all the outputs, you get a smooth plot like that. So that is the curve for that vector valued function. Let's try this one. R of t equals sine of t in the I direction and cosine of t in the j direction. So we also know that this one is going to be a 2D plot. Only two components. So let's try R of 0. So when we plug in 0 for t, we get sine of 0 is 0, right? Plus cosine of 0 is 1. So in this case, we get the vector 0i plus 1j. So that's going to be this point. That's 0, 1. Now let's do, because we're working with trig functions, I'm going to use radians as my input. So I'm going to jump to something like pi fourths. So I'll plug in pi fourths for t, and in this case we'll get sine of pi fourths, cosine of pi fourths, which is going to be, is that square root of 2 over 2? I plus square root over 2 j. So that is something like that. Now we can do pi halves. Which will give us sine of pi halves is 1, and cosine of pi halves is 0. So in this case, we just get this. We get the 0.10. Now you might be seeing the pattern here, and if I move this a little bit, move where I drew that a little bit this way. Oops, it doesn't want to move. This is actually the plot of the unit circle. So as you keep increasing t, it'll trace out a circle like this. And if you plug in t equals 2 pi, so r of 2 pi, that will give you all the way back to 0i plus 1j. So plugging in 2 pi gives you one full rotation, and you come back to where you started. And by increasing t further, you continue to trace out the unit circle over and over and over. Right, so as t goes to infinity, you just trace the unit circle over and over. Now you could imagine some transformations of this function, where if I put a coefficient, a scalar coefficient, in front of these two components, like 2 sine of t and 2 cosine of t, all that would do is increase the radius to 2. So it would instead trace out a circle that is twice as big. Or I could just do it to one of the components. I could do 2 sine of t, 1 cosine t, 1 cosine t in the j direction. And in this case, it would only double the I direction values. So in this case, it would actually only make it longer in the x direction, so it will kind of give you an ellipse. In this case, it would trace out an ellipse that looks like this. So those are some transformations you should become comfortable with these vector-valued functions. And now, this last one is a really important one to recognize and understand because it shows up everywhere in vector calculus. So this one is r of t is equal to cosine ti plus sine tj plus tk. So this one has 3 components. So we know it's going to be a 3-dimensional curve. And that's why I have 3 axes set up here with x, y, and z. So this one is also trig functions. So I'm going to plug in fractions of pi in for t, just to make it easy to calculate. So we'll start with r of t. Excuse me. We'll start by evaluating r at 0, which in this case gives us 1i plus 0j plus 0k. So it's just 1i. So we go 1 unit in the x direction. Let me make that bigger. Okay, so that's 1. Now you may notice that if I got rid, let me try to get rid of this. If I got rid of this k component, pretend it didn't exist, then that actually looks like the plot we just made. That cosine ti plus sine tj, that is the unit circle plot. So see how adding this k component, tk, changes the plot that we just did. So keep that in mind as we move forward. So let's do r of pi fourths. That's going to be square root of 2 over 2i. Square root of 2 over 2j. And tk, so it's just pi fourths. k. So what is that going to look like? So that's square root of 2 over 2 in the x and y directions. So we have this and this. That's our square root of 2 over 2 in both x and y. And then we get pi fourths in the k direction. So we go up however much you think pi fourths is. So like maybe that much. And so we can connect those smoothly like that. So now let's try pi halves. That will be 0i plus 1j plus just pi halves k. So what does that look like? 0i, 1j, pi halves k. So now we're 1 in the y direction. So that's like 1 in the I direction, or 1 in the j direction, and pi halves in the z direction. So that's something like up here. We'll say that's pi halves, twice as big as pi fourths. So this height is twice as much as here. So we can kind of continue to connect those. I'll do a couple more. Let's do pi. So r of pi is equal to negative 1i plus 0j plus pi k. So that's negative 1 in the I direction, and pi, the amount pi, in the z direction. So that's going to continue. So we do negative 1 plus pi. Maybe that's up there. So we're going to get that. And so really what we're doing is we're tracing out the unit circle, but increasing the height as we go. And the height is directly proportional to the input value because it's just tk. So in this case, if you kept going, you would continue to trace out the unit circle, or you would just keep getting higher and higher. So this shape is a helix. That's pretty cool. And if you were to look at it straight from above, or if you were up here looking down, it would look just like this plot here. You wouldn't be able to see the z component increasing as t increases. But if we draw it from this angle, you can see that when we add this third term, tk, that as t increases, k increases directly proportional. So you're just going to keep making this helix that goes up. Some transformations of this one that you should know are that if we did like 2tk, that this would double the rate it goes up. So in this case, it would be like stretching the spring twice as wide. Similarly, if we did like 1/2 t, it would compress the helix twice as much. So it would take this spring and it would compress it by a factor of 2. So those are some transformations that you can do with the helix. And then these scalar transformations also work for the helix as well. You can make the helix kind of like a more oval shape, or you can double the size or shrink it. Those are all transformations that apply. So differentiation is another thing that we can do with vector-valued functions, and it works very similar to scalar-valued functions as well. So to take the derivative of a function like r of t, we would write it like this. There's a couple different ways. You could use the Leibniz notation, which would look like this: d dt of r of t. So that's the first derivative of your function. That's equal to just saying r prime of t. And you just do it component by component. So to take the derivative of r of t, you differentiate component by component. So all of that's equal to, so r prime of t is equal to f prime of t in the I direction plus g prime of t in the j direction plus h prime of t in the k direction. So you just take the first derivative of the functions attached to your I, j, and k vectors. So that's pretty easy, and all the differentiation rules that we learned in Calculus 1 and 2 apply here as well. So the interpretation, right, we know that the derivative corresponds to a lot of physical applications, especially related to like particle movement. Those also apply here. So the velocity vector, right, we know velocity is the first derivative. That's the interpretation of it. So the first derivative of r is the velocity vector, right, and that's equal to, right, dr dt. So it's the first derivative of r. And that will be a vector that points in the direction of motion, right, the velocity, and the magnitude of it will be its speed. So I can draw a picture of what that looks like here in a second. So the instantaneous direction vector, that's just a vector that shows the instantaneous direction. So it's the velocity vector of length 1. So it has no magnitude, or it's just magnitude 1, and it just points in the direction. So all that is, oh, and that's equal to, sometimes we'll call that v of t for velocity. The instantaneous direction vector is the unit vector of the first derivative. So that's v of t divided by the magnitude of v of t. And that's a unit vector. Speed is just the magnitude of velocity. So speed is just v of t, the magnitude of v of t. And then acceleration, right, we all know that acceleration is the second derivative of position, which in this case, acceleration, we'll call that a of t, and that is the first derivative of velocity and the second derivative of position. So very similar to Calculus 1. I can draw a little picture of what that looks like. So we have some axes here. Let me just draw an example vector valued function. So I'm going to draw r of t in this orange color. And I'll make it look like this. So there's r of t. If I were to pick just a random point, like maybe right here, right, we know the velocity vector would look like this. It would point in the direction of instantaneous motion. So it is a tangent line. So it is tangent. And that is v of t. Now the instantaneous direction would be that vector, but a normal unit vector, right? So it would just be of length 1, so it might look like that. And that's v of t divided by the magnitude of v of t. So that's how that would look plotted onto a graph. So knowing that the velocity vector is always going to be tangent to your position curve at any point t. So that'll be useful here in this next example. So in example 2, we want to find the parametric equation for a tangent line to the curve r of t at the given value of t. Right, and so in this example, that was my chosen value of t that put us right here. So we're finding the equation of a line. So if you remember from last chapter, to write the equation of any line, you always need two things. Right, you need a point on the line and the direction. So we need to find those two things. So here's our curve, sine of ti plus t squared minus cosine t in the j direction, and then e to the t in k. And we're trying to find the tangent line on the curve when t equals 0. So that just tells us where on the curve we're evaluating this. So first of all, let's find the direction vector. So what direction the tangent line is. And we know that the velocity vector, right, the first derivative of position, is always going to be a vector that's tangent to the curve at that value of t. So let's just start by finding the velocity vector. So we'll find r prime of t. So what's that going to be? Cosine t, I plus 2t plus sine t in the j plus e to the t k. Now let's evaluate that at 0. So we're finding this is the general velocity vector. So this, you could plug in any value of t and get what the velocity vector is. But we're going to find the specific one when t equals 0. So that's going to end up being 1i plus, that will be 0j plus 1k. So another way to write that is just the vector 1, 0, 1. So that's our direction vector. The direction vector for the tangent line. So we found the direction vector. Now we just need to find a point that's on the line, and the easiest point to use is just the point on the curve that you're evaluating at. So the point we can use is just r of 0. That will give us the point of evaluation. So to find a point, easy to use r of 0. So the position vector at t equals 0 is just going to be negative j plus 1k. So that's going to be the point 0, negative 1, 1. So now we have the two things we need. We have the direction vector and a point on the line. So now we're going to construct our tangent line down here. So now we'll construct tangent line. And I'll call that L of t. And it wants us to write it in the parametric form. Find the parametric equation. So L of t is going to be equal to x is going to be the x initial position, which is 0, plus t times the x component of the direction vector, which is 1. So it's going to be 0 plus 1t. Y is going to be negative 1 plus 0t. And z will be 1 plus 1t. And so this right here is a parametric version of the tangent line to this curve when you're at the point on the curve corresponding to t equals 0.